Well, first of all, let me very much thank Claude LeBrun and the other organizers of the Geometry Festival this year. I've, of course, known about the Geometry Festival for many years, and I've always wanted to speak at it. But this is my chance. Of course, I would love to be actually meeting in person up at Stony, Brook, what we deal with, what we have to do with. So what I want to talk about is some relatively new results on Ricci Flow. This involves work with, first of all, with Chris Guenther and Eric Bahuaud, and some other work also with Natasa Sessum and Dan Knopf and Tim Carson. I want to start by saying a little bit about my history with Ricci Flow. As some of you may know, I was a physics graduate working on mathematical relativity. But as the custom is, when you're hired at one of the Pacific Northwest Geometry Colleges in schools, they invite you to give a PNGS talk. So in 1982, I was hired at the University of Oregon, and they invited me to the Vancouver conference of the PNGS. This was very fortunate because at that same conference, Richard Hamilton gave it a very important talk, which I think was really, in many senses, the birth of Ricci Flow. So what he proved was this theorem that says that if you have a three-dimensional Riemannian manifold, and if the initial Ricci curvature is positive, then the manifold must in fact be the three-sphere, and this result was proven using Ricci Flow convergence. My second encounter with Ricci Flow happened 3 years later at a general relativity conference in Florence. And at that conference, Workhorse presented a conjecture. So the conjecture was that if you look at the evolution according to Einstein's equations of initial data in this case consists of a Riemannian metric and a symmetric tube tensor. That if you smooth this initial data, then this might accurately model the general set of cosmological solutions of Einstein's equations. And this smoothing would be carried out using Ricci Flow. So this was never proven, but I found it very interesting. So as a consequence, a meeting with Markov, I invited him to Oregon. And so this started a collaboration with Markov and Martin Jackson. And what we were able to prove is the theorem that says that if you look at the Ricci Flow of so-called Gaudi type metrics on the three torus, and these are metrics with a T2 isometry and some other conditions. But what we can show is that the Ricci Flow of these metrics, it always converges to a flat metric. So the significance of this result is that I believe this was the first Ricci Flow convergence result for metrics which have both positive and negative Ricci curvature. We were able to publish this result in JGG. So there are actually, in a sense, two ways to think about Ricci Flow. The first approach is to think of it as an initial value problem for weakly parabolic PDE system where the metric evolves according to an artificial parameter. According to this equation, the top term of the metric is equal to -2 times the Ricci tensor of the metric, and I add an extra term, the so-called normalization term, which guarantees that the volume of this Riemannian metric stays positive over time. And what is starting at some initial Riemannian metric. The second way to think about this, Ricci Flow, is as a dynamical system. So if you consider the for fixed manifold Mn, if you look at the set of all Riemannian metrics, and if you look at each metric, then the Ricci Flow equation provides a vector space on that manifold, and the flow is just given as indicated in that picture. So of course, we know a huge amount about Ricci Flow, but I think probably the predominant set of results we know is for 2 or 3 dimensional Riemann manifolds. I think we're learning more and more as time goes on. But another set that we know a lot about is Riemann metrics on usually compact manifolds with fairly large isometry groups. This includes the result, which I said earlier about the Ricci Flow for so-called Guenther metrics. So the talk I want to give today involves 2 very different parts. The first part, which I call part A, involves what we call convergence, stability of Ricci Flow. And this is for both for flat geometries on the torus and also for hyperbolic geometries in the set of asymptotically hyperbolic metrics. So I'll first talk about that result. And this is work I did with Chris Guenther and Eric Bahuaud. And let me mention 2 important applications. The first is to show that if you look at Ricci Flow for initial metrics, which are near warp product geometries with no isometry at all. But if they're near, then if we look at the Ricci Flow of such metrics, then these flows always converge to a flat metric. The second application shows that if we look at Ricci Flow for the symmetric switcher and the rotationally symmetric asymptotically hyperbolic geometries, again with no symmetry at all, that these flows always converge to the basic hyperbolic metric. The second part of this talk involves what I'll call singularity formation, Ricci Flows for certain multi-warp complete geometries on non-compact manifolds. This is work done with Knopf and Natasa Sessum and Tim Carson. We have 2 important applications. The first application is that we can show that there's somewhat unexpected behavior of certain little sequences in Ricci Flow with solutions which form type 1 singularities at spatial infinity, with this emphasis being on the formation of the singularities and spatial infinity nowhere in the interior of the manifold. And what we could show is that some of these blowup sequences, subsequences form gradients shrinking, which is solitons. Not that surprising, but there are also other blowup subsequences which form ancient solutions, which are not solitons at all. And another application of this work is to show weak stability of generalized cylinders under Ricci Flow. So let me start by talking about this with the results on the what we call convergence stability for Ricci Flow. The basic idea is this: so if you have G sub infinity as a stable point for the Ricci Flow, either asymptotically a stable fixed point or just a stable fixed point, I indicate these 2 types of stability in these pictures. The one on the left is asymptotically. It's an asymptotically stable point. And the one on the right is just a stable point where the convergence is not necessarily to infinity, but to some kind of essential manifold. So that's it. So if we have such stable points and we let G naught be a metric such as the Ricci Flow with the initial metric G naught converges to G infinity. So given this situation, we say that a Ricci Flow is convergent stable at the stable point G sub 0. If there's a neighborhood which we call cap n of G naught such that for every metric G1 in that neighborhood, the Ricci Flow starting at G1 converges to G infinity or to a metric in the corresponding central manifold. So I indicate this in these 2 pictures again. The one on the left, we have a asymptotically stable Ricci Flow converging to G infinity, and so we look at G0, and we look at nearby metrics that the Ricci Flow, if it's convergent, stable will also converge to G infinity. And on the right hand side, I have a picture where instead of converging necessarily to G infinity, these nearby Ricci Flow starting near to G0 converges to the central manifold. Let me mention one example application, and another one later. So this first one says that since John Lott and Natasa Sessum showed that the Ricci Flow of warp product geometries, for example, of the circle of the torus at A, showed that they always converge to flat geometries. Since we can prove convergibility for Ricci Flow on the torus as I say T3, but this would hold more generally. It follows that if we look at Ricci Flows for metrics which are near the warp product, that these will also converge to either G infinity or to the central manifold. So here's the second application of these results. So since Eric Bahuaud and Eric Workhorse, they've shown that the Ricci Flow for rotation symmetric asymptotically hyperbolic geometries always converge to the hyperbolic geometry. And since we can prove convergent stability for Ricci Flow for asymptotically hyperbolic geometries, it follows that the Ricci Flow for hyperbolic metrics, which are nearly rotating, is symmetric but no symmetry as well. They must also converge to the hyperbolic geometry. So I wanted to discuss the basic ingredients for proving convergence stability for Ricci Flow. There are two of them. So the first is to prove that Ricci Flow for certain class metrics is either stable or asymptotically stable at G infinity with respect to some chosen topology, some function space. And then if we could also prove that the Ricci Flow for that same class of metrics is well posed in the sense of continuous dependence on the initial data that convergent stability follows. So let me talk about the specific case of convergent stability for Ricci Flow on interdimensional toruses and flat metrics. So as I just mentioned, we need to first of all prove a stability theorem at the flat metric, and second of all, we have to prove continuous dependence of Ricci Flow on compact manifolds. In this case, we need continuous dependence for arbitrarily large amounts of time. So to prove convergent stability around the flat metric on the torus I mentioned, we first of all need a stability theorem for such flat metrics. I think there are various cases of this, but I want to mention the result, which I proved with Guenther and Knopf a few years ago. So the theorem says that if we let HK alpha denote the level holder space of symmetric two tensor fields whose kth derivatives are alpha holder smooth, and if we let G infinity be a flat metric on the torus, then what we could prove that there is just a neighborhood and of that flat metric with the neighborhood defined using the level holder norm, such that the Ricci Flow G1 of T for any initial metric G1 in that neighborhood plus converge exponential to a flat metric, and not generally the G infinity, but to some flat metric on a central manifold. I want to mention some of the key ideas for proving this stability. They show up later in the talk as well. The first idea is that we relied on the so-called semi-group approach, which was carried out, which was explained by Bahuaud and Lunati. The second step is using Ricci determinant as a sort of shadow for the Ricci flow itself. I remind you that the Ricci flow is essentially the same as the Ricci flow itself, but it has also the evolution equation as a sleeve derivative term, where W depends on the evolving metric, as well as some pattern, as well as some background metric. The third step is to carry out the linearization of the Ricci flow. So for the perturbed metric, which we're calling the perturbation, which we call H. The time derivative of H is equal to the initial average, the Laplacian of H. So the fourth step of proving this stability theorem is to verify what we call what's we call the sectoriality of the linear Laplacian, which involves showing that the spectrum for this Laplacian forms a certain range in a left complex half plane. And then also part of sectoriality is to verify the boundedness of the resolvent of the Laplacian. And the sixth step is to verify that the right-hand side of the Ricci flow is both continuous and has a Fouché derivative, which is a Lipschitz. And then the seventh step is to verify that the diffeomorphism relating the Ricci flow and the Ricci flow is bounded. And this involves analysis of a certain harmonic map heat flow, which generates the diffeomorphism. I'm just being fairly sketchy, but this is all in the literature. So as I mentioned, to prove convergence stability, the first step is to prove a stability theorem, as I just discussed in the case of the torus. The second step is to prove continuous dependence for the Ricci flow on these manifolds. So let me state the theorem. This is work of Bahuaud, Guenther, and I from a few years ago, a couple of years ago. So if we have a compact rewriting manifold, which we call MG0, and if we let G0 be the maximal solution of the normalized Ricci flow, for T in some interval from 0 up to tau of G sub naught, which is maybe finite or infinite. And then again, T sub G naught denotes the maximum time of existence. And then if we choose a time less than this maximal time of existence, then there are just positive constants, which are called little r and caps C, depending only on the initial measure and that time interval such that if the difference between G1 and G0 with respect to this norm is less than or equal to R. Therefore, the unique solution, which starts at G1, the maximal time of existence satisfies G1, is greater than or equal to the time of tau. And we have the result that if we look at the evolutions of G1 and G0 with respect to the Ricci flow, that this is bounded by this constant times the initial data for all the time in the interval. So let me say a tiny bit about the terms which are needed to prove continuous dependence. First of all, we need short time uniqueness and continuous dependence. And in this case, we relied on some work of Lemma and Breadlove. And the tools for proving this are very similar to those tools used to prove the stability theorem. And then this only gave a short time continuous dependence. To prove the long time continuous dependence. This is work again of Bahuaud, Guenther, and I. We use an iteration, an iteration scheme where we show that on each of the intervals we have uniform short time with continuous dependence. We just carry the iteration all the way to as far as we need to get the continuous dependence for the long time that we need it. So combining the stability result with the continuous dependence is how we proved the convergent stability theorem for closed manifolds. Those again results of Eric Bahuaud and Chris Guenther and I a couple of years ago. The first result says that if we have a rebounding metric on a closed torus set, and the Ricci Flow converges to a flat metric under Ricci Flow, then for all solutions starting at nearby metrics, no isometry, assume necessarily converge also to flat metrics. We have another result, which I'll just say briefly, is if we look at the smooth closing bounding metric, and if we know that the Ricci Flow converges to a hyperbolic metric on a compact manifold, then under normalized Ricci Flow, that solution starting and nearby metrics also converge to G infinity. Again, in this case, we're working on a compact manifold. The result statement involves reminding metrics not on a compact manifold. So let me say a tiny bit about how you show convergent stability, given the stability and the continuous dependence result. So if we let G0 of t be the normalized Ricci flow of a particular metric, which converges exponentially to a stable fixed point flat metric, then it follows from the definition of convergence that within a finite time, the flow necessarily enters any specified neighborhood of G infinity, including that neighborhood in which all normalized Ricci flows must necessarily converge exponentially to G infinity or to a nearby flat metric. So now consider G1 metric, which is sufficiently close to G naught, then it follows from this continuous dependence result that for any specified finite time flow, G1 of t remains relatively close to the flow of G0, and therefore it must enter N. Then it follows from the G1 of t convergence, exponential converges to a flat metric, and then it must necessarily converge to G infinity or something on that set manifold. And that's our simple proof of the idea of convergent stability in this compact case. So I just discussed the convergent stability for Ricci Flows on this compact manifolds. I want to talk about these new results also with Eric Bahuaud and Chris Guenther just finishing up this year, which shows that we have convergent stability of Ricci Flow for asymptotically hyperbolic geometries. So what the theorem says, if we have this is the application of it, but let me state in this form. If we have a rotationally symmetric asymptotically hyperbolic metric with the same conformal infinity as a hyperbolic metric, then what we can show is that there's an open neighborhood, which you call n of that initial metric with respect to a specified weighted little Holm space for asymptotically hyperbolic metrics, such that the normalized Ricci flow with initial geometry G1 in that neighborhood must converge exponentially to that hyperbolic metric. So I want to give a very sketchy proof of the convergence stability in this case. So it's very similar to the idea of the proof of convergent stability on compact manifolds. But again, importantly, we're using certain specified little order spaces which are adapted to the asymptotically hyperbolic geometry. So first of all, we need a stability theorem for the hyperbolic metric. And in this case, we rely on some work of Babylon. Then we need to prove long-time continuous dependence for the Ricci flow for asymptotically hyperbolic geometries. And again, this is very recent work with Eric Bahuaud and Chris Guenther. And then we're also relying on the result of a few years ago, which proves the convergence of rotation symmetric asymptotic and hyperbolic geometries to the hyperbolic geometry work by Eric Bahuaud and Eric Workhorse. So I want to now talk about some completely different work, and this is work which I did with Natasa Sessum and Guenther and Tim Carson. So what we can show is that certain properties of singularity formation for Ricci Flow for certain multi-warp complete geometries on non-compact manifolds. The important motivation for this is exploring Ricci Flow solutions with singularities which form not an interior of the manifold spatial infinity, and we also want to explore a certain reachability result for generalized cylinders under Ricci Flow. So let me set up the what we're working with. So these are the certain multi-warp products which have Einstein fibers and manifolds. We're working first of all with the base manifold, which we call B sub n. B super n, and this is the dimension. We have the base metric, which we call GB. This is a complete non-compact embodied manifold. Then we have a set of, from 1 to kappa, of certain fibers, and each fiber we call F sub n alpha, and the metric we call GF alpha. These are a collection of Einstein space forms, and it's such that we have that the Ricci metric of these fiber metrics is equal to some constant mu alpha times the metric. So given a bunch of functions, mu alpha on the base manifold, positive functions, there's a certain warp product metric G on the manifold given by base manifold plus the fibers where we have the metric takes the following, takes the indicated form. We have the base metric plus those fiber metrics. So we have those functions mu alpha on the fiber metric. So to find the Ricci flow for these equations is relatively straightforward, but also quite tedious. So we have the time derivative of the base metric plus the 2 times the Ricci flow, 2 times the Ricci metric, Ricci curvature. So that's just equal to a certain non-homogeneous right-side spread charge on those functions U alpha. And then we have a heat-liking equation for the functions U alpha with again a right-hand side which depends on the square of the gradients. Again, it's straightforward to calculate this. It's somewhat tedious. And it reminds me of a comment by Cliff Tobbs where he called straightforward but tedious work called Where the Dead Horses Are Buried. So we have these special sets of metrics of these products of the base metric and the base manifold and the fibers. So there's a particular direct product solutions, and this will be very important as we go. And so let me point these out. So if we let these functions U alpha sub x, let them be constants, which we call A alpha. And if we write U alpha x of t, we write it as A alpha minus mu alpha, where mu alpha, recall, it comes from the Einstein metrics. Times c, then we find that this is an explicit solution of the second equation for as long as the flow remains smooth. Since we want to look at metrics which are perturbations of these special homogeneous solutions, we're going to set A alpha as the infimum over the base of the U alphas. We want to find a new function which we call V alpha. Again, this will be a positive value function on the on the base manifold. So we write V alpha is U alpha minus, let's say alpha n. I'm writing here as initial data. And then we can write a new form of the same set of metrics in this form, which is given by the space, the base metric plus the sums of certain functions type and times the fibers, as shown here. So to study the Ricci flow of these metrics, it's very helpful to define certain controlling functions which control the curvature. So we have gamma alpha, which is just the gradient of the V alpha squared, and then we have chi alpha, which is the Hessian of these V alphas, again squared, and then finally we have the third we call it rho, and this is a function which is given by the square of the Riemannian curvature. It's important to mention, to note that if we look at the Riemannian curvature of these metrics G and subtract from these the Riemannian curvature involving these fibers, that we can control this by constant times, these controlling functions, rho and gamma and chi. So the particular Ricci flows we're going to look at, we want to look at involve certain main function, main assumptions, which are assumptions on the initial metrics. So to do this, let me just say a little bit about certain parameterization functions. So the first set of functions we define, we have curve G alpha, where again alpha runs from 1 to the total number of set fibers. And these all have are controlled by a certain quasi-norm. So what we find is we look at the quasi-norm, that this is equal to the G of S divided by S squared, where S is just some parameters. Again, remember that these G's are functions from the positive real numbers to positive real numbers. So this quasi-norm is controlled by the super GS over S squared plus a certain sort of second order derivative, sort of quasi-norm as I indicate here with the norm to comma on active stuff. I write it here in detail. We don't need to worry exactly about what this is. So given the G alphas, we can further define what we'll call H alpha. And these are quite closely, they depend entirely on the choice of the G alpha. So the H alphas are given as a product of the G alphas times a summation of these G alphas over S squared. So we want to specify certain assumptions on the choice of the initial data of these multi-wall products. So our assumptions are that there exists a constant that we call C initial, and there exists a set of these functions G alpha, such that for all these fibers, first of all, we have that the norms of the G alphas are controlled by the C initial, and then we have these controls on these curvature control functions. We have the gamma alpha initial is controlled by the C initial times the G alpha's initial, and then we have chi alpha controlled by the C initial times the H alpha. These are composed functions with the initial choices of V alphas, and then we have the rows initial control by the C initial. We further assume that the initial the gradient of the curvature is bounded, and also there's at least one of these mu alphas which is positive. So that is at least one of these fibers, which has a part, which has positive curvature. So if we take metrics of this multi-multiplier form, and if we assume they satisfy these beta assumptions, we can say our theorem. I'm going to first give a somewhat non-technical version, and then I'll give a more technical version. So the first one says that, okay, if we're looking at a Ricci Flow solution for metrics of this form, it satisfies the initial main assumptions. Then we claim that there exists a constant which, such that for all time in a certain interval, the metric can be written in a certain form, which I write here first. It's just something times the initial base metric and then a something times the fiber metrics. Notice that we have the a alpha minus mu t insolence linear time, and then we also have a term which involves the initial data of the v alphas. So that's the somewhat non-technical version. Let me give the somewhat more technical version again. So again, we're starting with an initial metric which satisfies the assumptions I said above, that there exist constants such that the following are true. For that we can write the solution on the time manifold in terms of the metric of on the base manifold plus plus this again something times the metric on the fibers, which I've written in terms of a linear time of evolution plus v alpha. So this is a solution of the Ricci Flow, and then and we have curvatures found in spatial terms in terms of certain time intervals, and the up to the maximal existence of time. And a very important part of this is that the v alphas are all uniformly equivalent for the time of the existence. Particularly, we can write this set of inequalities involving the v alphas relative of the v alphas relative to the initial values of them. Also, part of this technical version of the theorem is that if we look at every point on the base manifold, and we look at the time in the time interval existence, one has these controls on all these curvature control functions. So we can show that rho is bounded about by the C initial plus a something linear time element. We also have certain linear time kind of controls on the camera and guide. These are a bit more complicated. I don't want to go into the details, but let's just say that we have these important controls on these curvature control functions. So these are two versions of the same main result. But very important is this following corollary, and that's if what we say is we take the same initial data satisfied the assumptions I said, that we can find data with equivalent initial data such that the Ricci Flow forms a singularity at spatial infinity. So what we say in particular is to exist initial data satisfy the main assumptions, which we say above with that same control constant, C initial the same initial values of V alpha and the same functions G alpha and H alpha, but with certain small changes in this constant A alpha, such that the conclusions of those theorems I said above and of all times. But most importantly, what we can show is that there are no singular points which occur in the main manifold and the singularity. It always occurs in this adjusted initial data. The singularities occur at spatial infinity in the wall type 1. And here I specify is the certain formula for the time of existence. So I want to say a little bit about how we prove both these the main theorem and also the corollary. So the first step is to show that based on the Ricci Flow equations, we can derive evolution estimates for those curvature controlling constant quantities. In particular, we show this constant, which occurs at n, which depends only on the dimensions. Such as we can write these equations for the curvature control quantities. Each one of them takes the form of a heat type equation with a right non-homogeneous radius. So, for example, the first one, for gamma alpha, the right-hand side involves the gradient of gamma alpha squared divided by gamma alpha and also gamma alpha divided. Notice that here I'm using the U alpha instead of the V alpha, but they again vary. It's easy to go from one to the other. So we have this evolution equation for gamma alpha. Similarly, an evolution equation for chi alpha and also for which take these forms. Again, probably too detailed, but I just want to show what the equations are. Notice the importance of this quantity average. I wrote right here down in terms of the curvature control functions. So in proving these results, so the first step I showed was to derive these evolution equations for the curvature control functions. The second step is just use the standard should top existing results for the Ricci Flow. So we know that the solutions just for a short time with certain curvature bounds. The third step is to prove a lemma which shows that with these curvature bounds on the short intervals and the evolution estimates for the curvature control functions, this produces a linear growth in time for the curvature control functions on a possibly short time interval, but with the important thing that the estimate constants depend on the curvature. So the fourth sketchy version of this proof is show that since we have linear time growth of the curvature control functions, this produces estimates of the curvature with it, importantly uniform constant. But again, we possibly have to reduce the time intervals to some extent, but we obtain these uniform constants. And these improved estimates with the uniform constants again, they bound the curvature linear in time. And the fifth step is to use an important open-closed argument to extend the time interval of the curvature estimates to the time of where the singularity develops. This again is an important part of the proof. So I just very sketchily said something about the proof of our main results. Now I want to say something about the corollary, which with small adjustments of that initial data to the constants, we can show that the singularities are type 1 and they occur at spatial infinity. So the sixth step is to show that we have bounds of the curvature control functions that's uniform to the singular time, that this implies that for t, which is sufficiently close to the singular time, there exist certain constants, which are called little c alpha, such that the Riemann curvature is given by this equation. And so since we know on a compact set that we have this formula for u alpha is equal to a alpha minus mu t plus v alpha x of t, that since we also know that the V alpha, that these are positive everywhere on the manifold, but we have infinity zero, it follows that we can write a formula for the soup of the U alphas in terms of the A alphas. This tells us first of all that the singularity must be a type 1, and also shows that the singularity cannot occur at on the base manifold. It must occur at the special infinity. So this shows the what we want to show that regarding the occurrence of these singularities, that they first of all type 1 and is occur at spatial infinity. So I probably shouldn't show you this, but it's somehow in our proof of these results we had a particular lemma which we use over and over in the course of proving our results. So I call it a workhorse lemma. I get dead horses, but let me forget about that. So what this thing says, it's a bit complicated, but let me state it a bit. So if we have a smooth solution of the Ricci Flow on some time interval, and we have a certain set of functions, u, v, and w, and they're all positive functions on the manifold, on this time interval. It's supposed to exist a certain constants, let's say capital C, since we have this these certain sort of heat-like equations on the left-hand side with in homogeneous section terms, where the velocity and the norms are all computed with respect to the solution of the Ricci flow. Then there exist certain constants which are listed such that we have again a heat sort of equation on all these functions u, v, and w. It gets somewhat complicated, but there exists a point on the base manifold and a constant c, such that we have these inequalities on the u, v, and v involving properties of the base manifold. We have this inequality of the u and v as zero with respect to the initial data as well as the evolution of the w. So again, somewhat complicated, although we use this number so much that maybe it might be useful somewhere else. But what it does, what it allows us to do, is to estimate a certain function u, which might be, say, a geometric quantity or a short time interval. We can estimate this in terms of a comparison function cap v, which might be a geometric quantity at the initial time, and a controlling function w, which might be, for example, a large constant, which depends on the curvature. So we use this quite a number of times. It was very important in our proof. So again, perhaps I should apologize for that last time, but again, we found it so useful. I want to state it, and you can see it in our papers. So what I want to talk about now is our first application, which is the main motivation for the whole. And this is that we found some unexpected behavior blowup sequences, solutions of Ricci Flow, when the singularities occur in spatial infinity. So we need some definitions. So first of all, let me define script R to be the soup of the three-mounting curvature of the metric as it falls on the manifold. We said that we have a singularity at some time t if we take the limit of the soup of R of t as the little t approaches cap t for its infinity. And then we said that a singularity is type 1 if the script R is bounded about by some constant bar divided by the time between the singularity and the time we're looking at. So we said that we have an essential blow sequence in a singular Ricci flow solution if there is a sequence of points pi and times ti on the manifold and the time interval, such that for some constant, we will see we have the remaining curvature at the center bar at the sequential points, which is bounded below by some constant divided by cap t, the singular time minus tr. And then we say that if a Ricci flow solution is type 1, and if a point P contained in the manifold is a limit point down under such a blowup sequence, then we say that P is a type 1 singular point for that particular flow. So there's very interesting and important result of at the smaller end topping, which shows that if a type 1 Ricci flow solution contains a type 1 singular point P, that for every infinite sequence, the corresponding rescaling Ricci flows in the usual form of rescaling then on a time interval, which goes from minus lambda jt to 0 if this sum converges. This not necessarily the sum converges to a normalized style, non-trivial graded shrinking solitons. That's a solution which I show here. That we have the Ricci convergent plus the Hessian of f is equal to 1 over 2 times the difference of the singular time t times t. And we also have that the time derivative of f is equal to the gradient of f squared. So that's a normalized non-trivial graded shrinking solitons. So they were able to show that if you have this type 1 singular point in the manifold, then we generally get such, we necessarily get these shrinking solitons. So what we can show in this work with Natasha and Dan and Tim is that we can find examples of a type 1 singularity, singular Ricci Flow solution with the singularity development and special infinity. No other Ricci Flow solution manifold app that it could have essential blowup sequences with some subsequences that do have a gradient soliton limit, and other subsequences that do not have a gradient soliton limit. And this kind of was worked on with Carson, Knopf and Sessum. So our theorem and the Corollary exhibit this. So what we show in the theorem is that exists complete non-compact kappa non-collapse Ricci Flow solutions with the manifold equal special case which is equal to the real number times the cos SP again. These develop type 1 singularities and special infinity, and on each of these solutions there exists essential blowup sequences along which a blowup Lemma yields a non-trivial gradient shrinking soliton, which soliton. There also exists essential blowup sequences along which no blowup Lemma can be a gradient shrinking soliton. And we have a corollary as well, which shows that under the conditions stated in that theorem above, that there's a blowup limit of the flow along a particular sequence going to infinity. And this is a non-trivial gradient soliton if and only if we this particular equation for the limit of these remaining curvatures. So this we use to distinguish those subsequences which form a gradient shrinking soliton and those which do not. So the metrics we look at in these particular examples are this fairly simple. So the metric is simple. So again, we have the base manifold. In this case, it's just a real number, real line. So we have the metric is equal to tx squared plus the certain functions times the certain fibers. We choose initial conditions on these functions v1 and v2. Certain of the metrics satisfies the base assumptions which I stated earlier so that the singularity occurs at a particular time and occurs in spatial infinity. So there are, to finish showing what's going on here, there are some results from Sigurd Hagenan and Knopf which show that for metrics of the particular form I just showed you, E, intended gradient is strictly Ricci solitons if you only have the curvature of the Ricci Flow solution satisfies the condition which I just stated. And then by construction, find that there are some subsequences of this essential blowup sequences of this Ricci Flows which do satisfy the converging condition of the code. And there are the subsequent sequences which do not satisfy this converging condition. So therefore we get subsequences which form this gradient, which are solitons and others which do not. So I want to mention another application of these results we have. So this gives us a very weak stability of the generalized cylinder of the Ricci Flow. So there's results of important results of Colding causes that proven a strong stability for the mean curvature flow for embedded cylinders. So as a corollary of our main results, working again with Dan Knopf and Natasa Sessum and Tim Carson, we can prove that the following weak stability theorem for Ricci Flow solutions, they're generalized cylindrical metrics. So here's a theorem. So we choose M to be R K plus P sphere for positive integers KP, and we said the solution metric, cylinder metric on them is given by this particular the Euclidean metric plus a constant times this fair metric for some constant A. So we can show that if we look at the Ricci flow for this initial metric, the cylindrical metric, it has a very simple form which becomes clearly becomes singular at the time t is equal to a star. Now, if we choose a real function, a real valued function, which is called delta vector, such that the perturbed initial metric, which I write in this form here, gx initial is equal to metric plus this function ux initial times sphere metric with the initial metric given by a star plus delta alpha. And if this satisfies the beta subset indicates appropriately in a spatial infinity, then we can show that the Ricci flow of this perturbed initial data develops a type 1 singularity spatial infinity at the top, a star that satisfies this particular stability condition, namely that if we take the soup of the time between 0 and the singular time of the flow gx of t minus the cylindrical flow that we have this control relative to the initial data. So there's one other thing that I want to talk about. It's the instability of generalized cylinder. So the other which can Ricci Flow, but I'm guessing that I probably run out of time. So I appreciate your attention. I appreciate your putting up with my voice. And I'd love to hear any questions you have about these results. And thanks again.